welcome to a presentation on gas chromatography. Today we are exploring this essential analytical technique used to separate chemical mixtures based on their volatility and boiling points. These are our list of contents, which is organized into several key sections to help you follow our study.
Gas chromatography is a technique for separating components based on their volatiles, which is differences in boiling point. In gas chromatography, the components of a vaporized sample are separated after partitioning between a mobile gaseous phase and a solid or liquid stationary phase held in the column. So gas chromatography has two types, which is gas-liquid chromatography, GLC, and gas-solid chromatography, which is GSC. For GLC, the mobile phase is gas and the stationary phase is liquid. For GSC, the mobile phase is gas and stationary phase is solid.
Now, let's dive into the fundamental principles of how gas chromatography actually works. You can think of this as a 5-step journey to our sample. It all starts when the sample is injected into the injection pot. This is where the process begins. Almost immediately, the sample is vaporized into the column. Because GC deals with gases, we need that liquid sample to turn into a vapor state instantly. Once vaporized, the sample is transported through the column by the flow of an inert gaseous mobile phase, often referred to as the MP. This carrier gas acts like a conveyor belt pushing the molecules forward. As the mixture passes through the column, the different components interact with the stationary phase inside. Some molecules move faster and some move slower. Finally, the separated components emerge from the column and are detected electronically by detector, which converts that physical presence into digital bits we see on our results.
For objective, we have 4 objectives. First is to determine the retention time TR of N-butanol and 2-propanol. 2 is to identify the components present in a standard mixture based on the TR. 3 is to identify the components present in unknown sample. And the last one to determine the effect of temperature on TR and RS. Methodology. This is the layout of our gas chromatography system, showing how we separate and analyze our sample. First, the carrier gas flows through a regulator to push the sample through the system. We inject the sample into the injector port where it vaporizes. Next, it then enters the column inside the oven. Here, the different components separate based on how fast they travel through the coil. As they exit, the detector identifies them and the results are displayed as a graph on the computer. These remaining materials are then moved to waste.
So gas chromatography is used to separate and analyze volatile compounds in a mixture. Now I will be talking about the functions of gas chromatography. Starting from the left, the carrier gas acts as the mobile phase and carries the sample through the system. The gas flow regulator controls the flow rate to ensure consistent separation. The sample is then introduced through the injector port where it is rapidly vaporized. The column placed inside the oven is where separation occurs based on volatility and interaction with the stationary phase. The oven controls the temperature to improve separation efficiency. So, as the compounds exit the column, the detector detects them and converts them into electrical signals. Finally, the computer system processes the data and displays the result as a chromatogram.
Let's go into result and discussion. This slide shows the chromatogram for 2-propanol analyzed at 70 Celsius. So from this chromatogram, we can see that 2 peaks were observed. The main peak appears at a retention time of 2.724 minutes with an area of 99.98%, which represents 2-propanol. This shows that the sample is almost pure. And the second peak at 3.626 minutes has a very small area of 0.017%, which may be due to a minor impurity or background noise. So their short retention time is because 2-propanol is highly volatile. So if the column temperature is increased, the retention time will decrease, but peak separation may reduce. And if the temperature is decreased, the retention time will increase and the resolution will improve.
Moving on to our result for butanol, please take a look at the chromatogram and the data in Table 2. In this trial, we identified these three distinct peaks. Peaks 1 and 2 appear very early at 2.659 and 2.926 minutes. However, this represents only a tiny fraction of the sample, less than 1% combined. The major peak, which is clearly visible on the graph, occurred at approximately 6.043 minutes. This peak accounts for 99.85% of the area, confirming the high purity of our N-butanol sample. Why does N-butanol elute at this specific time? When we compare this to our early standard mixtures, N-butanol has a significantly later retention time. This is primarily due to its physical properties. First, it has a higher boiling point compared to the early eluting compounds, and second, it has a lower volatility, meaning it spends more time interacting with the stationary phase inside the column rather than staying in the carrier gas. This result perfectly demonstrates how GC separates substances based on their boiling points and chemical affinity.
This slide shows the chromatogram of the standard mixture at 70 Celsius. So from this chromatogram, we can see that there are three peaks indicating three different compounds in the mixture. So for the first peak, it appears at 2.692 minutes with an area of 36.98%. And the second peak appears at 2.929 minutes with a very small area, which is 0.012%. And the last peak appears at 5.903 minutes with the largest area of 63.01%, showing that this compound is less volatile and interacts more with the column. So increasing the column temperature will reduce retention time but may cause peaks to overlap. And decreasing the temperature will increase retention time and improve separation, but the analysis will take longer.
Moving on to our results for the standard mixture, you can see the data summarized in Table 4. Upon analysis, we observed 4 distinct peaks, which indicates that there are 4 separate components that is present in this mixture. So, each of these peaks has its own unique retention time, ranging from approximately 2.27 minutes to 3.29 minutes. And this shows that we achieved a very good separation for each component. It is also important to look at the peak area percentage, as this represents the relative amount of each component in the sample. So in this case, peak 4 has the highest area at over 62%, identifying it as the major compound in our standard mixture.
Okay, so for this standard mixture, peak 1 represents one of the main components present in a significant amount. Another peak represents the main component of the mixture, while peak 3 is present in a very small amount. The clear and well-separated peak shows that the chromatography works well and the standard mixture can be used to help identify unknown samples. Okay, so for the conclusion, gas chromatography was successfully used to separate the components in the samples. Different compounds showed different retention times based on their volatility. The standard mixture produced clear peaks, showing that the method worked well. By comparing retention times, we were able to identify the components in the mixture. Overall, gas chromatography is a useful technique for separating and identifying compounds in a mixture.
These are some of the references we used for this study.